Hello, welcome to QCT's Expo Hall Talk at 2020 OCP Virtual Summit. My name is Dustin Wu, Director of Telco Solution Engineering at QCT. In this session, I'm going to share our vision on data center trends, challenges, and opportunities. Let's get started. This chart shows the trend of CPU performance growth on the world's top 500 supercomputers during the past 25 years. The trend clearly indicates that the computing performance is growing faster and faster at an exponential rate over the years. CPU running at higher performance means that it would need additional power to drive the increased performance. Based on an industry-wide study, the electric power consumed by data centers worldwide has reached 198 terawatt-hour in year 2018, which amounts for 1% of global electricity usage. The chart on the left indicates that the overall power consumption in data centers worldwide stays flat in the past few years. This is due to better power efficiency design applied to the IT equipment. The chart on the right side indicates that more and more workloads in data centers have been migrated from traditional data centers to hyperscale and cloud data centers. As of today, Moore's law holds true in the semiconductor industry. That is, more die are being fit into a smaller chip space. However, the physics of required more power to support higher circuitry density also remains true. Therefore, increased power consumption is expected on the key components of a computer system. It is predicted that all the major components in the IT equipment will consume more power, as shown on this chart, while the electrical engineering technology continues to evolve. Given this trend, we need to try every way to compensate the ever-increasing power consumption in order to keep the Earth green. After all, the overall resources on Earth are not unlimited. Therefore, besides the top 500 list index, which was used to compare the computing performance of supercomputers, the Green 500 list was established to measure the greenness of supercomputers. It emphasizes on computing efficiency, that is, performance per watt index. That number can be further translated into money savings, which is the performance per dollar index. The traditional way to cool down the IT equipment is to use air cooling technology. The cool air runs from one end of the chassis and flows to the other end of the chassis. Depending on the design scheme, hot spots can be formed at different locations on the system. The orange and red color areas on this slide indicate the hot spots where good heat dissipation design is required. In summary, when the CPU and other components on the high-density computing systems are consuming more power, the traditional air cooling mechanism will not be adequate to dissipate the heat generated by those power-hungry components. So, what can we do to solve this issue while we are still building more and more powerful computers? Liquid cooling is the answer. Taiwan 2 is a supercomputer built by QCT at the National Center for High Performance Computing in Taiwan. It consists of 252 servers. Each server accommodates 2 Intel Xeon SB Gold CPU and 8 NVIDIA V100 GPUs. In total, we have 504 Xeon CPU and 2016 GPUs running AI applications. The heat dissipation required for this supercomputer is enormous, such that the traditional air cooling mechanism may not be able to handle. QCT adopted an innovative liquid cooling technology on this supercomputer. The whole system is kept cool to maintain efficient operation by the coolant injected from the tank located on the top of the rack. The computing performance of Taiwan 2 reaches 9 petaflops, which is ranked as number 21 on the top 500 list, according to the ranking published by top500.org in November of 2019. In the meantime, Taiwan Near 2 is ranked at number 12 on the Green 500 list. With the liquid cooling technology, it is projected to save $8,464 per server during the 5-year life cycle of this system, which is translated to the savings of up to almost $79,000 for the whole rack, comparing to using the traditional air cooling technology. PUE stands for Power Usage Effectiveness, and DCIS, Data Center Infrastructure Efficiency, are the two indexes used to measure how efficiently a computer or a data center uses energy, with DCIE being the inverse of PUE. A PUE value of below 1.2 means very efficient in terms of power usage effectiveness. Taiwan Near 2 scores a PUE rating of between 1.09 and 1.12, which is classified as a very efficient supercomputer system. The same liquid cooling technology that was used on Taiwan Near 2 has now been applied to the QCT servers that are designed to support high-density GPU nodes running performance-hungry AI applications. Today, AI applications are used in many areas to transform the way people live, work, and play. Here are a few examples. Here are some more examples in the smart manufacturing industry, financial industry, and so on. Basically, AI is everywhere. As we look back at the AI technology evolution history, we found that initially all the computation was done on the CPU. As the performance demands increased, varieties of technologies surfaced to help accelerating the computing performance. That includes GPU, FPGA, special purpose ASICs, and etc. QCT has deep engagement with major accelerator vendors to enhance the hardware to boost the performance of AI workloads. Today, 5G services are emerging. The major characteristics of 5G applications are high bandwidth, mass connectivities, and low latency. Many 5G services at the edge of network rely on AI to reach the targeted performance level. Therefore, we can see a nice blending of AI workloads and 5G applications. QCT recognizes this trend and has been striving to offer diversity of hardware platforms to deliver the end-to-end solution for the 5G and AI applications. Starting from the right side of the chart are the skills designed to support AI training and computing-intensive video applications. Moving forward to the left are skills intended for supporting various workloads in regional data center. Further toward left are specific skills designed to support RAN, multi-access edge computing, and AI inferencing workloads at the indoor edge. Moving further left is IP65 compliant hardware to meet environmental requirements of outdoor applications. At far left side of the chart are the universal CPE devices designed for workloads running at customer premises. In the next few slides, we are going to share details of a few selected models listed here. Let's start with the 52BE. It is a 2U server that offers scalable computing power at the edge. This server provides NUMA balance features optimized for high-performance computing on a dual-socket system. It supports up to 3 terabytes memory and 7 PCI expansion slots to provide sufficient I/O throughput for the fast-growing computer demands at the edge. This is the front view of the D52BE. The depth of this chassis is 580 mm, which can be fit into a smaller data center. This is the server model that QCT has been shipping to Rakuten Mobile Networks for building the world's first fully virtualized mobile network. QCT is the exclusive supplier of hardware platform in that project. Next, let's look at the D52Y. It is a 2U server specifically designed for telco edge use cases. It provides OIO access on the front. With physical dimension of 400 mm in depth, it can be easily fit into the edge data center, where the physical space is rather limited. Other telco-centric design considerations including -48-volt DC power and AC power inlets at both front and the rear sides of the chassis. It is the performance grade upgrade for the vRAN and MEC applications. Here is the close-up front view of the D52Y NVMe SKU. It can host up to 10 small form factor tool-less hot swappable drive bays and 2 full height and half-length PCIe cards. Here is a close-up front view of the D52Y GPU SKU. It provides space for up to 5 PCIe cards plus 2 small form factor tool-less hot swappable drive bays. It can host up to 4 NVIDIA Tesla T4 GPU or 2 NVIDIA Tesla V100 GPU. With the AC power sockets on both the front and rear side of the chassis, it allows you to flexibly route the power cables to fit the layout of your data center. It also comes with 5 tool-less hot swappable fan modules. Next, let's look at SD2H1U server. This server offers ultimate I/O flexibility for lighter weight applications running at the edge. The dimension of 400 mm in depth makes it an easy fit into a relay rack in the edge data center. Like D52Y, OIO accesses are on the front, which is essential for telco applications. Here is a front view of the SD2H. There are system status LEDs, 4 10G Ethernet ports, 1 gigabit Ethernet port for management, a couple of USB 3.0 ports, and 1 micro USB console port on the front panel. Let's take a close-up view into the flexible modular design on SD2H. On the networking inference SKUs in the above, the PCIe slots can take one double width GPU card and another FPGA, NIC, or SAS methylene card. On the cache accelerator SKU at the bottom, it can take one full height half-length PCIe card and 2 15 mm U.2 drives. On the rear side, it comes with 2 AC sockets for flexible PSU power routing and 6 hot swappable fan modules. It also supports optional Wi-Fi LTE modules for universal CPE applications. Up to this point, we've discussed about how we used accelerators to boost the performance of AI workloads. However, it may not always be necessary to use accelerators. With the enhancement in the CPU technology, you may be able to utilize the power of an advanced CPU to achieve the performance target of your AI workloads. One example is the Intel Vector Neural Network Instruction Set, also called VNNI. VNNI is supported on the latest generation of Intel processors. Intel Cascade Lake SP CPU supports the VNNI instruction set, which can perform an effective job to boost the performance of AI workloads. QCT has worked with Intel to validate that. The results were verified on a Quanta Grid D52B1U server with hardware configuration shown on this slide. In the first benchmark, we ran ResNet 50, which is a convolutional neural network deep learning application with TensorFlow software framework on the server with VNNI enabled in the CPU. We received the result of having 2,271 images inferenced per second. That number is twice as many as the results received on a system without VNNI support. During this exercise, We also found that by tweaking the settings of several BIOS parameters, it can produce the optimal performance during the benchmarking. Please note the BIOS setting highlighted in the red colored text. In the second benchmark, we ran the ResNet 50 with Intel's OpenVINO software framework on the VNNI-enabled system. In this case, we received another 30% performance gain compared to the result obtained from the previous exercise. What this means is that there are multiple factors that can influence the performance grade of an AI workload. These factors include CPUs, instruction sets, software framework, BIOS setting, etc. Hence, before you conclude on what you need to do to speed up your workloads, it is suggested that you examine the whole problem context. Then you may be given the opportunity to choose the best solutions for the problems that you are trying to solve. That is all for my presentation. Thank you very much for taking the time to attend this session. If you have any question about QCT's products or are interested in learning about what additional QCT can offer, please come to visit QCT virtual booth. We look forward to interacting with you. Together, we can explore ways to build the best infrastructure of the future for your advanced IT and CT solutions. Have a nice day. Bye-bye.